Welcome to Opportunity Crude's Management Seminar Series, an informative look at crude processing challenges. Disclaimers. The purpose of the OCMS series is to provide refiners with the latest information in processing opportunity or price-advantaged crudes, such as heavy sour oil, oil sand bitumen, light tight oil, and highly acidic crudes so that they can make better decisions in light of a volatile oil market. Opportunity Crudes Management Seminar Series Video Number 7, A Lot of Problems, Fouling and Corrosion, Part 2 Corrosion. As mentioned in our previous videos, certain crude quality and blending practices have caused concerns for refiners due to potential problems from cheaper crudes. Corrosion is one of two major problems refiners face when processing certain crudes and blends. It is estimated that corrosion costs U.S. refineries about $3.7 billion a year. According to the 100 largest losses by Marsh & McLennan companies, the refining industry suffered $2 billion worth of losses related to corrosion damage alone over the 5-year period from 2007 to 2011. These problems have led to an increase in demand for corrosion inhibitors in the United States, which is expected to increase to a demand worth $2.5 billion by 2020. In today's video, we will discuss corrosion in the crude tower overhead, including recent incidents involving refinery corrosion, the mechanisms and causes behind different types of corrosion, desalter operations to mitigate corrosion, crude tower corrosion case studies, and monitoring and treatment options to prevent corrosion. Because corrosion is a broad topic, this video will focus on corrosion in the crude tower caused by contaminants. Discussions related to corrosion caused by acids will appear in the February seminar, Your Corrosive, Naphthenic Acid and High TAN Crudes. Navigate oil market uncertainty and supply disruption in refining at the 6th Opportunity Crudes Conference in Houston, Texas in the U.S. from October 22 to the 24th, 2018. The theme of the conference is Crude Disruptors, Accelerating Changes in Global Refining. Higher oil output and refining price advantage. Domestic light tight oil has benefited international oil majors and U.S. independent refiners in the first quarter, respectively, according to just released earning results. Unfortunately, the good news will end soon as the oil market is going to enter an uncertain time since the price rout in mid-2014. A dark cloud is forming as driven by two formidable forces, geopolitical risks and changing supply-demand fundamentals. Change is not new in the refining world, but disruption of crude sources could significantly upset overall refinery operations in terms of crude management, processing, and product quality and volume. Our attendees will learn from conference speakers and network with colleagues on how refiners can navigate present market uncertainty and crude supply disruption by devising better business strategies, finding ways to increase operational flexibility, and adopting new technologies to turn challenges into opportunities. As in our previous meetings, this conference is expected to be highly productive and rewarding because of excellent speakers, timely theme, well-organized agenda, and stimulating atmosphere to encourage exchange of ideas. 5 topical sessions in 2.5 days include: Session 1, Global Oil Market Outlooks, Geopolitics, U.S. Pro-Export Policy, OPEC Strategies, Peak Demand. Session 2, Challenges and Opportunities in Oil Trading, Exports, Imports and Infrastructure Logistics. Session 3, Crude Contaminants, Incompatibility, Blending Strategies Amid Changing Feedstocks. Session 4, Flexibility of Light Tight Oil Processing and Bottoms Upgrading to Make Products in Demand. Session 5, Big Data Analytics and Emerging Adoption of Internet of Things in Crude Selection, Management, and Refining. In this celebrated biennial meeting, you will meet colleagues from many companies around the world. The Opportunity Crudes meeting from October 22 to the morning of October 24 is coordinated with Crude Oil Quality Association's fall meeting, which will be held on October 24 and October 25 to benefit from synergy in serving our upstream, midstream, and downstream colleagues. To save up to $300 before June 1, register today by visiting opportunitycrudes.com/Houston 2018. Here is a preliminary agenda for the 6th Opportunity Crudes Conference. In August 2014, a Midwestern 413.5 thousand barrel per day refinery in the U.S. underwent a shutdown caused by leaks in the overhead pipes leading to the CDU. The leaks were believed to be the result of corrosion due to acid and sulfur content in the Canadian crude it processes. In April 2013, a U.S. refiner that previously had an incident involving a corroded pipe in 2012 and later improved inspection procedures, found a similarly corroded pipe in a different refinery. This pipe was replaced with a new pipe containing silicone that would resist corrosion, potentially preventing another incident. The Occupational Safety and Health Administration, or OSHA in California in the U.S. approved a new safety regulation governing state refineries on June 7, 2017. The new regulation, which will be added to Title 8 of the California Code of Regulations as Section 5189.1, will require state refineries to conduct damage mechanism reviews for equipment for material degradation, such as corrosion and mechanical wear. Many refineries in the state are said to have already adopted a number of the practices required under Section 5189.1. Nowadays, refiners are often pressured to process more challenging crudes. These low-priced crudes may contain higher amounts of contaminants that contribute to corrosion. Salts, acids, and dissolved gases in crudes often form corrosive species during processing. Hydrochloric acid is believed to be the greatest contributor to refinery corrosion. According to PermaSense, when refiners often adapt process operations in the top sections of the atmospheric tower to produce less naphtha and more valuable distillates, more corrosion is often observed. When refiners attempt to cut costs by reducing or eliminating proper prevention and monitoring measures, corrosion problems arise. Both metal and non-metal contaminants in crudes can cause corrosion in refineries. Our previous seminars, What's in Your Crudes, Parts 1 and 2, discuss these contaminants in detail. There are both natural and artificial sources of these corrosion-causing contaminants as well as certain crudes that may contain more of these contaminants. There are methods and commercial analyzers refiners should use to detect these contaminants and possibly prevent corrosion issues. Certain metal and non-metal contaminants, which include calcium, iron, nitrogen, organic chlorides, sodium, and sulfur cause corrosion. The following table lists problems associated with these contaminants, including corrosion in various regions in the refinery. In today's seminar, we will discuss how some of these contaminants contribute to different mechanisms of corrosion. Certain contaminants and compounds in crude oils may form corrosive species during processing. Salt residues, such as chloride salts, can pass through the desalter and form hydrochloric acid in the atmospheric and vacuum heaters. Nitrogen oxides form from the refining of crudes with nitrogen compounds, which can cause steel corrosion when cooled in the presence of water. When ammonia reacts with hydrochloric acid, it forms ammonium chloride, which is corrosive. Corrosive sulfur species include mercaptans, which naturally occur, and hydrogen sulfide formed from decomposed sulfur compounds. Certain changes in crude quality and the crude tower overhead can lead to increased corrosion rates. Increases in the amount of hydrochloric acids and other mineral acid species such as organic acids and weak acids, as well as changes in the formation temperature of ammonium chloride and ammonium chloride salts, increase corrosion rates. According to a computer model of the CDU distillation tower overhead system from a study by PermaSense, various factors, including water dew point temperature and location in the system, vapor-liquid equilibrium behavior of ionic species as water condenses, conditions such as pH and concentrations at the initial water dew point, and the thermodynamics and kinetics of amine and ammonium chloride salt formation, affect corrosion rates. Overhead aqueous phase corrosion occurs due to the formation of acids, in particular hydrochloric acid, in the presence of water. This type of corrosion often occurs in crude units, vacuum units, and hydrotreater stripper units. This type of corrosion is most severe at the dew point, and the temperature where this occurs depends on the partial pressure of the water and the absolute pressure of the system. Hydrochloric acid forms when hydrogen chloride gas dissolves and when organic chlorides thermally degrade. Hydrogen sulfide can react with iron chloride to form hydrochloric acid. Electrolytes can also form sulfuric acid, which is also highly corrosive. Corrosion can occur in overhead condensation systems when ammonium chloride deposit into its surface. Ammonium chloride is formed when ammonia and hydrochloric acid react. This type of corrosion is common in overhead lines, trays of the column, pump round lines and condensers. Because ammonium chloride become adhesive even in the presence of a small amount of water, it will accelerate corrosion activity due to underdeposit metal loss. Ammonia is often used as a neutralizer, but should not be used for crudes with a hydrogen sulfide concentration exceeding 20 to 30 parts per million. In water-based systems, such as amine systems, multiple species can produce corrosive compounds. Carbon dioxide has a high solubility and can form weak acids in amine-based systems. Carbon dioxide also increases corrosion by forming salts with amines used to remove acid gases, hindering their ability to reduce corrosive compounds. Hydrogen sulfide can corrode iron and form ferrous sulfide. While the ferrous sulfide can actually protect against further corrosion, it is easily removed by high velocities and stronger ions. High-temperature corrosion occurs with certain species at very high temperatures at above 205 degrees Celsius. Reactive sulfur compounds and naphthenic acids are the causes of this type of corrosion. Typically, at temperatures above 260 degrees Celsius, high-temperature sulfur corrosion occurs. Sulfur species that cause corrosion include active compounds such as mercaptans and hydrogen sulfide formed from the degradation of other sulfur compounds. Years of experience in dealing with corrosion in the refinery have led to observations involving the material compositions of refinery equipment and surfaces and corrosion rates. Increased sulfidic corrosion has been seen in pipes with insufficient amounts of silicon. Chromium content in steel has also been noted to be an important factor in protecting against corrosion. Finally, regions of severe service such as the atmospheric tower overflash section and vacuum tower wash section may require a careful selection of construction material. Good desalter performance represents a refiner's best chance in preventing corrosion. It is the desalting process where contaminants that may ultimately lead to corrosion, such as chlorides and amines, are removed. According to Dorf et al., lower corrosion rates occur when desalter efficiency is increased. Refiners must consider how the crude they are processing affects the desalter. Heavy Canadian crudes, in particular, contain large amounts of contaminants that produce more stable emulsions and increase salt levels. Refiners may need a larger desalter and chemical additives to process these crudes. Crudes with high amounts of calcium naphthenate, such as DOBA from Chad, reduce desalter efficiency by shorting out electrical potential in the desalter. High levels of oxygen in desalter wash water may react with hydrogen sulfide and form sulfuric and sulfurous acids, increasing corrosion. There are measures refiners can take to prevent issues with the desalter and downstream. With crudes with high conductivity such as those with large amounts of calcium naphthenates, refiners should reduce the grid voltage if the design of the desalter permits, adjust the emulsion breaker to reduce amperage, and reduce the fraction of the conductive crude. Organic chlorides often pass through the desalter, but if refiners improve contact during mixing, they can potentially catch these thermally unstable, difficult to detect chlorides, amine salts and amines formed from scavengers, both of which cause corrosion in the CDU, can be protonated by adding an acid upstream of the desalter to form an ionic species that more easily partition to the water phase and into the effluent brine. Finally, Refiners can reduce corrosion problems with oxygen in the wash water by limiting concentrations to less than 1 part per million or to 20 parts per billion. In the crude tower, the distillation unit is comprised of the pre-flash tower, atmospheric tower, and vacuum tower, regions that are all susceptible to corrosive species. When amine scavengers used to treat hydrogen sulfide is used, tramp amines may form. These tramp amines can react with hydrogen chloride and form corrosive salts that can deposit in the CDU and cause under-deposit corrosion in the CDU and various parts of the crude tower. Under-deposit corrosion from corrosive amine salts have rates about 10 to 100 times faster than naphthenic acid corrosion. Refiners have shared experiences of corrosion in the crude tower. At an American Fuel and Petrochemical Manufacturers Conference, a panel member from HollyFrontier said atmospheric tower corrosion mostly comes from inorganic acids such as hydrochloric acid, while the vacuum tower overhead typically suffers from low pH corrosion when processing high-tan crudes. An attendee from CH2M Hill mentioned that while pre-flash drums pose an insignificant corrosion problem, for pre-flash towers with separate overhead systems from CDU towers, corrosion is more of a concern because water partial pressure in the atmospheric tower overhead will greatly increase, resulting in severe liquid phase chloride corrosion. At the 2013 American Institute of Chemical Engineers, a speaker from Petrobras suggested to reduce chloride content in vacuum diesel, the fractionation reflux rate in the vacuum pump rounds should be raised. A U.S. refinery in South Texas experienced more corrosion after processing an increased amount of light tight oil from the Eagle Ford Formation. This practice led to an increased formation of tramp amines, leading to salt corrosion in overhead bundles. If multiple bundles were to fail, this would result in an unplanned CDU shutdown, possibly costing the refinery more than $4 million a day. According to the refinery, corrosion issues can be minimized by adding caustic and increasing the minimum hot drum temperature. A refinery in the Gulf Coast once experienced 3 CDU shutdowns over 2 years caused by corrosion in the pump around exchanger overhead. While an analysis of the deposits found amines from the neutralizer and the plant amine from the refinery acid gas removal unit, surprisingly, amines from MEA scavengers used to treat hydrogen sulfide upstream were found. This led to increased salt corrosion. Even though the refiner had good chloride control and desalter performance, amines from MEA scavengers still caused salt formation and subsequent corrosion in the tower top pump around section. A company developed a technique to create salt formation curves to understand and prevent corrosion due to salt formation in the overhead of the crude unit. The company analyzes output data from its ionic equilibrium model at various operating conditions to develop these salt formation curves. Ongoing amine mapping and amine speciation is also performed to determine which amine is driving the salt point to determine salting frequency. Once salting frequency has been established, operating conditions are optimized to ensure reliable operation of the CDU overhead. A vendor and a refiner worked to develop a salt point operating envelope to manage salt formation in the atmospheric tower, allowing the refiner to set the tower top operating temperatures in a safe range to prevent corrosion while also increasing distillate production from the tower. Based on the developed salt operating envelope, the refiner was able to see the amount of time salt was being formed in the tower based on operating conditions. Because the point at which the tower transitions from not forming salt to forming salt is a function of both the acid and base, the refiner was recommended to better manage both amine concentrations and chlorides in the overhead. The refiner later developed key performance indicators to optimize operating conditions, allowing simultaneous management of overhead corrosion and increased diesel production from the atmospheric tower based off the results of this salt operating envelope. Refiners and companies have worked together to determine causes of corrosion. In 2009, Irving Oil and Baker Hughes worked together to study multiple corrosion mechanisms occurring at once, mainly hydrogen sulfide corrosion and ammonium chloride corrosion, and corrosion caused by increased flow velocity. The cause behind these problems was determined to be a combination of crude type and operating conditions. In 2016, PermaSense used a combination of sensors and computer modeling to determine the root cause of increased overhead corrosion at a European refinery. Nalco Champion used this data to calculate changes in process operations that contributed to corrosion. Major U.S. oil refiner Chevron and the University of Saskatchewan teamed up to conduct a series of experiments to find a way to better assess crude oil corrosiveness. The idea behind this was to use X-ray technology to quantify and identify sulfur compounds that cause corrosion. The technique called sulfur K-edge X-ray absorption spectroscopy uses medium energy or tender X-rays that allow refiners to collect data on sulfur species and add them to a library to better identify corrosive compounds. The goal of corrosion monitoring is to intervene when a defined critical level of corrosion occurs. There are a number of versatile monitoring tools available to control corrosion to allow optimization of the chemical treatment program. These include electrical resistance probes and polarization resistance probes, hydrogen flux monitoring, ultrasonics, eddy current, acoustic emission, thermography, radiography, etc. However, it is recommended that refiners use continuous monitoring programs that provide a steady stream of information. These programs are commercially available and, when used with computer modeling and software, could possibly help refiners predict corrosion. Industrial Internet of Things, or IIoT, is a technology yet to be embraced by the oil sector but has been suggested as a way to identify hidden corrosion. Here is a non-inclusive list of corrosion monitoring programs available on the market. Additional information on these companies' technologies and on products previously mentioned can be found in our just-published strategic report entitled Novel Strategies of Processing Price-Advantaged Crudes in a Volatile Oil Market. Here is our sponsor's experience. According to Baker Hughes, a GE company, the TopGuard Overhead Corrosion Control is an engineering and chemistry-based program to manage the risks associated with crude unit overhead system corrosion. The first step to managing corrosion is to understand the underlying cause. Only then can a mitigation strategy be devised. A well-designed monitoring program is the third, critical step in the process, enabling the operator to quantify the benefits achieved by the mitigation strategy. At the heart of the TopGuard program resides the ionic model. The ionic model is a thermodynamic-based process simulation technology that provides critical elements of the entire corrosion management process. The model provides clarity on the mechanism of corrosion at work, root cause. The model then provides a platform to assess the many mitigation options that can be considered, and once a mitigation plan is implemented, the ionic model provides the Corrosion Risk Monitor or CRM, a field-based tool to monitor and continually assess the ongoing risks of corrosion, providing advance warning when conditions lead to an increased risk of corrosion. A wealth of refinery-provided input data feed the CRM, and past experience functions as a great teacher. The TopGuard approach provides a systematic means to understand, mitigate and monitor overhead system corrosion. As opportunity crude processing becomes more prevalent, corrosion risk in crude unit overhead systems is increasing. The TopGuard program provides a means to counter the ever-increasing corrosion risk by defining a mitigation path that is most cost-effective. Companion programs that help manage corrosion risk are found in BHGE's Crude Oil Management Approach, a suite of desalting tools and technologies that unleash the capabilities of the crude feed system. Featured elements are the Xeric heavy oil demulsifiers and Excalibur amine removal. The TopGuard program also features a unique engineering technology for design and optimization of wash water systems. The TopGuard spray model, the industry's only mass transfer-based tool for water wash design. The TopGuard Ionic model can define the most effective operating envelope for managing corrosion risk. The TopGuard Overhead Analyzer provides real-time data to feed the CRM. And specialty chemistry is another facet of TopGuard. patented, blended amines for neutralization of acids, corrosion inhibitors for processing opportunity crudes, and salt control additives are all part of the suite of tools that make up TopGuard, the most advanced technology available for overhead system corrosion control. There are a number of measures to reduce corrosion. While refiners could use corrosion-resistant alloys in equipment, this option is often economically unfeasible. Instead, ensuring that the desalter runs efficiently to remove as much contaminants as possible is the best measure to take. When challenging crudes contain a large amount of corrosion-causing contaminants, refiners could use chemical additives that remove contaminants such as chlorides and amines. Caustic injections are often recommended to reduce overhead chlorides. In the overhead, refiners could also set the pH to a range of 5.5 to 7 to stop corrosion from hydrochloric acid. Wash water can also be used to dilute salts and acids. According to Dorf et al., when looking for treatments such as corrosion inhibitors and amine neutralizers, refiners should look for those with certain properties. Corrosion inhibitors should not form emulsions in and instead be highly soluble in naphtha, diesel, and kerosene. They also should have very good film consistency and be able to work in pH conditions from 2 to 9. Amine neutralizers, on the other hand, should have a neutralizing strength stronger than ammonia, distill overhead at low temperatures, and be able to dissolve in water as it initially condenses. The salt formed from the neutralization reaction should not be hydrocarbon soluble, have a low melting point, and do not form solids. The dry salt of the neutralizer should tend to absorb moisture from the air and form a liquid with small amounts of water. Here is a non-inclusive list of companies that sell corrosion inhibitors. With the increased processing of cheaper and opportunity crudes, crude overhead corrosion from crude contaminants is becoming a major problem. Corrosion severely hinders refinery operations and the problems resulting from it are costly. Refiners must be aware of the contaminants that create corrosive species and crudes that may contain more of them. Refiners must also be vigilant for crudes that affect desalter performance. The desalter is a refiner's first line of defense against corrosion by removing a majority of corrosion-causing contaminants, and refiners must ensure that this unit is capable of handling the incoming crude. Refiners may often need to use chemical additives, such as corrosion inhibitors and salt dispersants, to augment corrosion control. In some cases, specialized alloys can be used to prevent corrosion in certain equipment and locations. In addition to these steps, it is recommended that refiners use a continuous monitoring program to detect corrosion quickly. Today's seminar discussed refinery overhead corrosion caused by contaminants such as salts and gases. Our next seminar, video number 8, Your corrosive, naphthenic acids and high tan crudes, will further expand on the topic of corrosion and discuss corrosion caused by naphthenic acids and high total acid number. Join us in February for our 8th video for a further discussion on corrosion. Thank you to Baker Hughes for sponsoring this video. Sponsorship opportunities are still available for the rest of the seminar series. Please contact Matt Wonder at mwonder@hydrocarbonpublishing.com to sponsor a future video. Sign up today to receive our quarterly technology newsletter, Worldwide Refinery Processing Review. Since it was launched in 1998, the review has become the most authoritative and comprehensive publication of the latest refining technologies around the world. The review monitors commercial technology developments and competition, plant operation improvements and troubleshooting, and R&D trends for all processing units, from the front end to the back end, in a single source. Each issue covers 2 technology topics with the following sections: market and technology trends and opportunities, state-of-the-art technology, plant operations and practices, refining R&D alert, worldwide installed capacity, recent construction activity and completed construction projects, latest refining technology developments and licensing. As shown in the table, this year's subscription will cover 8 topics, 2 in each quarter, apart from an annual subscription of the review. Individual quarterly issues and individual technology topics are also available for purchase. For more information, contact us at review@hydrocarbonpublishing.com. Here are upcoming crude oil quality events. Here are upcoming crude oil quality events. Your comments are appreciated. Please send your comments to info@opportunitycrudes.com so we can enhance the value of upcoming seminars. Disclaimers.